So today's topic was BB-84 protocol, right?
Yes.
Okay, so let me. Okay, so there are two parties, Alice and Bob. So what they want to accomplish is they want to share a uniformly random string. This is like their secret key. And, you know, on top of being uniformly random, I guess uniformly random from the point of view of any other sort of eavesdropper that is trying to break into their communication. The key should also be it should be known just to the two of them. It should be uniformly random and private. And is it clear to people why we would want to accomplish this, first of all? Okay, you know, call this key, you know, S. And S is some n-bit string. Okay, so S is some string of n bits, say. And yeah, so the goal is once they have this secret key, then they're able to communicate, with sort of utmost security. And, you know, I'll be a bit more precise what this means. So I haven't seen Eric's lecture. So, you know, if there are things that don't quite make sense, so Eric, you can intervene if I'm straying away from.
For sure.
So, yeah, so they can communicate with utmost security, meaning, you know, anyone who drops into their conversation, their communication, even with unbounded computational power, will not be able to see what they're sending to each other. Okay, so usually when you do, you know, the cryptography that protects our credit cards, you know, RSA, you might have heard of the RSA encryption. All of these schemes are sort of secure only against computationally bounded adversaries. So in the real world, you can assume that adversaries are computationally bounded, right? Even if they have a really big computer, the scaling of how much time it would take them to break your encryption with respect to sort of the length of the say the key or you know some security parameter scales very badly for the adversary, like exponentially. So if you increase the sort of the length or some parameter of your encryption scheme by just a little bit, you make it so much harder for an adversary to break it. You know, if the adversary, on the other hand, is computationally unbounded, then, you know, all of RSA encryption and most of this, the encryption used on the internet would be broken. Okay. Now, having a uniformly random private key allows Alice and Bob to actually communicate in a way that is secure, even against a computationally unbounded adversary. There's nothing that you can do to actually break this. And the scheme that they can use to do this, did you show them this, Eric, the one-time pad?
Did I show them the what?
The how to use this key to communicate securely?
Yes. Yes, so we went over the encoding in a random basis and
Oh, but did you show them the one-time pad, like how to use the key that they obtain to do encryption?
No, I did not.
Okay, so then I can touch upon that.
Yeah, that'd be great.
So once Alice and Bob have a secret key S, what they can do is the following. Okay, so say Alice, so it's called one-time pad encryption. This is a completely classical concept. Okay, there is no quantum in the one-time pad encryption. Okay, the quantum part is in obtaining the secret key S. But once you have the secret key S, you can use it as follows. You know, say Alice wants to send a message M. Okay, which a message M, which is of the same length as the secret key S. Okay, which is known by the secret key is known by Alice and Bob. Okay, so then what Alice does, you know, is Alice would create a ciphertext, call it C, as the same length as M and S. Okay, so C, Alice would take it to be M plus S, well, XOR S. So what I mean by this is, you know, let me give you an example. So let's say that the length of S and M is 3, okay? So for example, you know, M would be the message 010. And of course, you know, you can encode any message you want, like any, you know, let's say the message could be, you know, let's get ice cream at 4 p.m., right? Any message of that kind can be written in binary, right? Okay. So here we're working in binary. So let's say the message is 010, okay? And the secret key is, let's say, you know, 110, okay? Then the ciphertext will be the bit by bit sort of XOR of M and S. So you do 0 plus 1, or 0 XOR 1, 1 XOR 1, 0 XOR 0. Okay, so you're taking sort of the parity of the sum. Let me just write down what the ciphertext is. So this would be 1, 0, 0, and this is your ciphertext. Okay, so this is the kind of the encrypted message that you send in the clear for everyone to see, right? The point is that only Bob will be able to decrypt this ciphertext and make sense of it. Okay, I'll say in a moment how this is done. Yeah, I have not very well understood the whole thing about how Alice will send the secret key to Bob. Okay, so let me, yeah, so far we have not said how Alice is going to send the key to Bob. Okay, I am just motivating why you would want Alice and Bob to share a secret key in the first place. Like, why would they want to have a uniformly random private key? That's what I'm motivating in the first place. And the reason for this is that you can do something called one-time pad encryption, which gives you the best possible security that you could hope for. It's not conditioned on an adversary having limited computational resources. Even with infinite time, an adversary cannot break this encryption. And the encryption is as follows. So if Alice wants to send a message M of n bits, and the string is also n bits, okay, so let me say here, n bits of length. The string S is also n bits. Alice creates a ciphertext C by taking the bit by bit XOR of M and S, like I did here in the example. So is it clear how C is derived from M and S? Very good. Nice. Okay, so this is the encryption part, okay? The encryption part. Okay, now there's a decryption part, okay? This is the decryption, where, you know, Bob receives C. I mean, C is communicated in the clear, like anybody can listen and see C. You know, but in particular, when Bob receives C, you know, Bob will do the following. Bob will sort of compute, say, well, M prime, okay, let's say, which is equal to, you know, C that he just received plus the secret key. right? Of course, Alice and Bob both have the secret key S. You know, they are the only ones who have the secret key S. So when Bob receives C, he would sum again, you know, take again the XOR with S, okay? And what I claim, my claim is that, you know, this M prime here that Bob obtains by summing S to the ciphertext, it's actually equal to M. In other words, Bob has recovered the original message that Alice wanted to send. So let's get ice cream at 4 p.m. I should have asked you, I made a mistake. I should have asked you, what should Bob do to recover the message that I should have asked you. Unfortunately, I told you already. AB plus A equals B, right? Yes, exactly. That's how Khurshad is saying, right? So because we're only caring about parity, you know, if I do A, you know, we obtain C by doing M plus S, you know. If we sum S again, you know, it's like M plus S plus S. Yeah, exactly. And S plus S is equal to 0. So you're left with M. Is this part clear? Yeah, exactly, Khurshad. Is everyone happy with this, with why Bob is recovering M? Yeah, awesome. And so anybody, you know, has some kind of intuition as to why this scheme here, if you assume that Alice and Bob have a, you know, they share a uniformly random private key S, okay, it's only known to them, nobody else. Does anybody have some intuition as to why this particular encryption scheme here is unhackable? Meaning anybody who sees C, like the ciphertext C, cannot do anything to recover the message M. Does anybody have any intuition about this? Who wants to take a guess? Yeah, so let's say, so when I say unhackable, okay, that's a very good question, Khurshad. So when I say unhackable, I mean that the probability, okay, what I mean is that the probability of hacking it, but this is a probability, right? It doesn't depend on how powerful you are. I mean, the probability of hacking the scheme will become negligible as you scale the size of the message up. That's what I mean. Meaning, you know, of course, you know, if the message is a single bit, there are only two things it could be. So of course you can guess it. But what I mean is that any adversary who tries to guess M, okay, the probability that they guess it right will be, say, exponentially small in the size of the message N. So it's as if, you know, you're not gaining anything at all. You might as well just have, yeah, so you might as well just have guessed, you know, at random the message M in the first place, right? So you can always randomly guess what M is going to be, and you have 1 over 2 to the n, 1 over 2 to the n, right? Your probability of guessing it right, if n is the length of the string that the message that you're sending. So you can always guess it at random and guess it with this probability, 1 over 2 to the n. What I claim is that if I use this scheme, you know, 1 over 2 to the n is actually the best that an adversary can do. So they gain nothing by looking at the ciphertext. They might as well just guess uniformly random. So it's the best that you can hope for, right? An adversary can always guess at random. An eavesdropper can always guess at random. But I'm saying if you use the scheme, you know, that's the best that an adversary can do. Just guess uniformly at random, and sort of make a random guess for what M is going to be. Yeah. So does anyone have an intuition why that might be the case? No, so I want the intuition as to why, if you know, you're an eavesdropper, right? If you see the ciphertext C, Okay, why can I not guess M? Why is my advantage, you know, my best probability of guessing M? Why is it 1/2 to the n? That's what I want you to argue. No, okay, so yeah, so Kieran, I agree with you. If you know, if I'm just randomly guessing the string, I think we can all agree that yeah. So I agree with all of you. So if I were just randomly guessing the message M, the probability would be 1/2 to the n, right? Where the length n is the length of the message. Okay. But now, right, I can do, you know, in principle, if I'm an eavesdropper, I don't have to randomly guess. You know, I could try to break the scheme. You know, I can, you know, drop into the communication, recover C, this ciphertext C, and maybe C allows me to do better than randomly guessing. Maybe there's a strategy that I can use to recover M, you know, with probability 1, no matter how long M is. You know, maybe there's something I can do. So I agree with you. If I were to randomly guess, it'll be 1/2 to the n. But here, the eavesdropper does get something. It gets the ciphertext. So maybe that helps him to recover M. So I want you to argue that seeing the ciphertext does not help the eavesdropper. That's what I want you to argue. Does that make sense? Yeah, Jakub, yeah, you have the right intuition. So basically, you know, what is the probability distribution of this? Yeah, you have the right answer. So what is the probability of this ciphertext C? I mean, this ciphertext C. Oh, sorry, you wrote it 5 minutes ago. Oh, I'm so sorry. I missed that. So sorry. Yeah, so the point is that the distribution of this ciphertext C is actually uniformly random because, you know, for any message that it could have been, there is some value of S that would produce, you know, that would be consistent with that message. And because S is uniformly random, it doesn't favor any particular message. You know, any message M has the same same probability of being the special message M. Or another way to put it is, you know, say Alice, there are 2 messages that Alice is going to send. You know, even if Alice tells you, I'm going to send you either M0 or M1. These are 2 messages. It tells the eavesdropper, I'm going to send Bob either M0 or M1. And the eavesdropper, all it has to do, even if the eavesdropper knows M0 and M1, the eavesdropper just has to guess which message has been encrypted by Alice, M0 or M1, even knowing M0 and M1. And the point is that the distribution of the ciphertext C that the eavesdropper is going to see is exactly the same in the 2 cases, whether you're encrypting M0 or whether you're encrypting M1. You're seeing exactly the same distribution over the ciphertext C because of because S, the secret key S, is uniformly random from the point of view of the eavesdropper. Okay, good. Anyways, I think this is something that you can think about more on your own if it's not clear. So, okay. So now I've motivated why we want Alice and Bob to share a secret key in the first place. Okay. Now let me go over the BB-84 scheme. So what Alice will do the following first. She will sample some strings of n bits, you know, A and B. So these are uniformly random n-bit strings. So A and B are n-bit strings, and I denote by AI and BI the bits of, you know, so AI is the ith bit of A, BI is the ith bit of B. So Alice will create a state of n qubits. There's this state here, where psi you know, psi 0, 0 is equal to 0. Then psi 0, 1 is equal to 1, and psi 1, 0 is equal to plus, psi 1, 1 is equal to minus. So in other words, the first entry, you know, the A basically tells me the basis that I'm encoding the qubit in. So either Hadamard or sort of standard basis. Okay. And the second bit, the B's, tell me whether I'm encoding the qubit in the 0 state or the 1 state, or the plus or the minus. Okay. Does this state here make sense? What this state here is? So the AIs are going to tell me the basis choice, so Hadamard or standard, and the B tells me whether I'm having the 0 plus or the 1 minus.
So the notation I used before was just that you have a bit 0 or 1, and then there's a subscript H if it was encoded in the Hadamard basis. So 0 subscript H corresponds to the plus state, and 1 subscript H corresponds to the minus state.
Okay, let me use that notation. So the AI tells me whether it's Hadamard or standard basis, and the BI tells me whether it's the 0 / plus or it's the 1 / minus. So you're creating these n qubits, right, for I = 1 through n. And you're sending all of these qubits to Bob. Yeah, AI is the basis, right? So let's say that AI is either, so AI is either, let's say, standard or Hadamard. And then BI is either, well, 0 or 1. So I mean, we're just defining sort of, I'm just literally defining this notation where 0, 0, and 0, 0 is equal to 0. 0, sorry, 1, 0 is equal to 1, and then 0, 1 is equal to plus, 1, 1 is equal to minus. Yeah, but if it helps you to, then BI is in terms of AI, sure. Or I can define this notation here like this. Like I'm defining this notation to mean this. Does that make sense? Okay. So now what Bob does, I believe, is Bob measures, makes a uniformly random choice of basis. Okay, so Bob, samples a basis choice, call it A prime. This is also an n-bit string. And you should interpret this as a choice of basis, right? So A prime has n bits. If the ith bit is 0, it tells me that the ith qubit is going to be standard basis. If the ith bit is 1, it tells me it's the Hadamard basis. And then after that, Bob sort of let's say, let's do qubit by qubits, okay? If, for I equals 1 to n, okay, Bob does the following. If a prime I is equal to 0, just measure, okay? And if a prime I is equal to 1, so 0 meaning standard basis, and 1 meaning Hadamard, okay? Then Bob will apply H first to the ith qubit, and then measure. Okay. So basically, Bob is kind of, sampling uniformly random choice of basis for each of the n qubits. Okay. Basically a guess for what, the actual basis chosen by Alice is. Alice chose made a choice of basis, right, denoted by A, right? This n choice is denoted by A. Bob is making, some guess of A, by sampling uniformly at random, another sort of choice of n basis, okay? And then sort of if the basis choice for particular bit I was standard basis, Bob will just measure. If, A prime, the ith bit of A prime is 1, meaning sort of Hadamard, Bob will first apply a H, okay, and then measure. Then Bob, so let's say that, the outcome of this n measurements is some string B prime. Bob reports this string B prime back to Alice. Okay, this is a string of n bits again. These are the outcome of all of the n measurements that Bob has made. Okay. And Bob also reports the choice. Oh no, sorry, I said it wrong. So you don't report B prime. You report your choice of basis, right, Eric?
You report the choice of basis in this formulation.
Yeah. Mm-hmm. So, okay, so, and so there's a check that they have to do publicly, right? On some of the, on part of the qubits. How does the protocol go exactly?
Yeah, so they will check whether they measured in the same basis, and if they did, that bit will become part of the string S. And if they didn't measure in the same basis, there's no guarantee that Bob would have obtained the correct bit, so you can throw that part out.
Okay, but don't they have to check? Don't they have to check whether the qubits have been tampered with? Like on
Yes.
a part of the, so there's some subset of the n bits, probably right, n over 2 of the basis choices will match between Alice and Bob.
Right.
Okay. Then on, say, half of this n over 2, they have to check, they announce publicly their measurement outcomes. Well, Bob announces B prime. Yeah. For this particular, and then Alice checks that they match what, her original encoding.
Right. So
right?
to protect against Eve, they have to compare some values. Yeah.
Exactly. So okay, so Bob will report A prime. Okay. So more or less, A prime is Bob's choice of basis. The string A prime, which is n bits, will agree with A. on approximately n over 2 bits. So approximately n over 2 basis choices are the same, okay? And out of this n over 2 choices in which the bases agree, Alice, say picks n over 4. So Khurshad said, I didn't understand the part about the bases being communicated. Okay, so Bob is making a choice of bases and then communicating this choice of bases to Alice, okay? Now, an eavesdropper that sees the choice of bases. Okay, so let me back up. So the reason why they're communicating the choice of bases is that, so two reasons, okay? So that they know which are the qubits that have been encoded in the same, so they know on which choices they agreed. So which are the qubits that Bob has measured in the correct basis that was chosen originally by Alice, okay? And out of this, out of the qubits that Bob has measured in the correct basis, okay, they will compare their outcomes on part of this, say half of this. And on this, outcomes they expect, on these measurements, they expect to get the same, have gotten the same outcomes. So maybe this is the point that I can make clearer. So let me go on this page, right? So if Alice has prepared the state plus, okay, now, yeah, they need to work on, so they need to work on a significant number of qubits, Jagrid, so n, right? And the idea is that the kind of the probability that the adversary can hack the key will be exponentially small in n. So they need a big number, n. That's correct. So let's say that Alice, to make one point clear, let's say that Alice is encoding a particular qubit in the S plus, okay? So plus means, that AI is the Hadamard basis, so 1, okay? And BI is 0. Okay, this is what plus corresponds to. Okay, now if she were to send this to Bob, okay, now if if Bob picks the same basis as Alice, okay, so Bob is applying, remember Bob is applying Hadamard, which means, apply Hadamard and then measure.
Are you writing something? Because we can see.
Oh,
if you are writing something, we can see.
Yes, I'm always writing something. Okay, so sorry about that. So let's say Alice is sending a state plus, which means, the choice of basis is Hadamard, so AI is equal to 1. The bit B, BI is 0 because we're choosing plus. Okay. Now, if Bob picks A prime I, happens to pick A prime I equals to 1, okay, which means Hadamard, so they're making the same choice of basis, then as specified by the protocol before, Bob will apply H and then measure. Okay. So what this does is, Bob applies H to plus. Okay. this gives him 0, right? Because h applied to plus is 0. And then when he measures, you know, he's going to obtain outcome 0 with probability 1.
I'll just jump in. So this would be the same thing as effectively measuring in the Hadamard basis. Applying a Hadamard and measuring in the computational basis, the same thing. It's just measuring whether the state is plus. These are equivalent descriptions of what's going on. So.
Yeah. So so another way to say it is to measure, as Eric said, in the Hadamard basis. Although I think in this course we've only sort of really talked about that.
I was vague on that, and this makes a lot more sense. So
yeah. And so okay, so if Alice and Bob make the same choice of basis, okay, then the outcome obtained by Bob, which is this 0 here, you know, this b prime I is equal to 0. Okay, this b prime I, okay, is going to be the same as bi, right? They're both 0. Okay, so whenever Alice and Bob measure in the same basis, they're going to obtain the same outcome. Okay, so what they're going to do in the next step is they're going to first check, you know, which are the bases on which they agree. So Alice is going to check, because Bob is sending the choice of basis along with the outcome. Well, not the outcome. She sends just the choice of basis. Okay. Alice is going to sort of single out which are the bases on which they agree. Okay. And then they're going to compare their outcomes on, say, about half of the qubits on which the bases agreed. So when they compare their outcomes there, they expect to get the outcomes to be the same, right? Because the choice of basis was the same. If the outcomes are not all the same, they know that something has gone wrong, that the adversary has tampered, the eavesdropper has tampered with something. On the other hand, if on the outcomes that they compare, you know, these outcomes are all the same, then they're confident that nobody has tampered with their qubits as they were being sent along from Alice to Bob. Okay. Once they're confident that the compared outcomes are all the same, you know, they still have left, you know, a small portion, say n/4 of the qubits, n/4 qubits. Okay, let me write it properly here. Okay, so there are approximately, you know, n/2 qubits on which basis choices agree. Okay. Then there are n/4 qubits which are used to publicly compare outcomes and check that these outcomes obtained by Alice and Bob, well, the BI and the BI primes, they match exactly. Okay. If this is the case, then Alice and Bob are confident that nobody has tampered with the qubits. Okay. And then there are remaining n/4 qubits for which, you know, the basis choice was announced, but not the outcomes. So these BIs are never sent. Okay, they're only sent, you know, the n/4 sort of B primes that are used to compare, these are sent over. Whereas the remaining, you know, n/4 qubits, the outcomes BI and BI primes have not been shared publicly. Okay, and so for the remaining n/4 qubits which have not been so whose outcomes have not been publicly announced, these are used to generate the secret key. So the outcomes for these n/4 qubits on which the bases had agreed, and they were not used to compare and check that the eavesdropper has not tampered. And these remaining n/4 sort of outcomes are what Alice and Bob output as the secret key, you know, that they agree is the secret key. They don't announce it publicly, they keep it for themselves. And they, with high probability, this, you know, this string sort of S, which now is length n/4. Okay, this string S coming from here that has length n/4 bits with high probability, you know, Alice and Bob are going to hold the same key. And this is how they do it. It's going to be uniformly random because the, you know, the BIs chosen by Alice at the beginning were uniformly random. And so this is the protocol. I know it was a bit fast, but I don't know if it made sense notation-wise with what Eric had said before. I can answer some questions if that helps. Is there any way to make this more efficient? Not if you want to preserve the sort of, you know, remember at the start I said that this string S, the secret key S that Alice and Bob end up having at the end, is really has sort of the utmost security, right? It looks uniformly random to an eavesdropper. You know, they can use it to do encryption with utmost security. If you want to keep this level of security, which is called information theoretic security, you know, it's secure even against computationally unbounded adversaries, you actually can't make it more efficient than this, or much more efficient than this. The only way that you can make it more efficient is if you restrict the computational power of the adversary, and then you start using tools from some tools from cryptography. But there you sacrifice this sort of information theoretic security. Does Bob use? Mm-hmm.
Of course, Alice and Bob have to check bits with each other to guarantee that there's no eavesdropper. What guarantees that you have to check half of them, or n/4 bits?
So it doesn't matter, the exact fraction doesn't matter, but as long as you check constant fraction of the bits. So there's, I mean, this is a kind of a probability argument. If you're interested, you know, these are called sort of concentration inequalities. So it doesn't matter the exact fraction, you can check, you know, n/100, n/10, as long as, you know, this doesn't change the behavior for large n. Okay, so if you assume that your n is large, then all of these things, it doesn't matter the exact fraction. So the reason is, I mean, I can only give the intuition, right? So you have, okay, you have this n/2 bits, you know, or qubits on which the base is agreed, okay? And so you want to gain confidence that, you know, just by checking n/4 of these pairs of outcomes, you want to gain confidence that the remaining, you know, n/4, if, you know, if all of the n/4 agree, you want to gain confidence that the remaining n/4 also agree. Okay, so you want to sort of check randomly, you know, a subset of these pairs of outcomes in which the base is agreed. Okay, and you're going to check this publicly so that you can gain confidence that what you don't check satisfies the same condition, meaning the outcomes agree. Okay, and there, you know, there are some sort of standard probability argument that you can make to say that if, you know, you check a constant fraction, say n/4, n/10 of these pairs of bits, and they all agree, okay, then sort of the probability that there is some pair of outcomes in the things you haven't checked that do not agree is small. It's something like this.
Right. So that's maybe one way to improve the efficiency a little bit if you're willing to decrease the percentage of bits that you share publicly. Then you have more part of your string, but then you're slightly less confident that there is no eavesdropper.
Exactly.
It's a trade-off.
Yeah. That's correct. No, so after you check, right, in order to check, you have to, Alice and Bob have to publicly announce respectively the BIs and the B prime Is. So basically, they will not use, those bits that have been publicly announced. They only use their BIs and B prime Is for the portion of indexes that have not been used to check, because these have not been publicly announced. So those BIs and B prime Is, because they've not been publicly announced, I mean, they're only known to the two of them. So they're private. They're also uniformly random because the BI were chosen uniformly randomly by Alice